Basketball is one of the most popular sports in the world. People often call themselves as hoopers when they have dedicated the whole life into balling. In this video, I'm gonna take the ball is life into a whole new level. If playing basketball all day long is not enough to show the passion for basketball, what about spending never-ending hours on studying the science of basketball? Although studying science of basketball won't make you become a good player overnight without practicing, it'll increase the efficiency of your training and shorten the time it takes to become a good baller. The video will demonstrate the science of basketball in ascending difficulty level. Let me see how many levels you can reach. Science of basketball level 1, quadratic functions. Look at the trajectory of the ball in the air. It seems like some sort of curve. Mathematically speaking, this trajectory is called parabola, which is the graph of quadratic function. Around 400 BC, Chinese and Babylonian already figured out to solve it by completing the square. In modern STEM class, we have learned that quadratic function can be described by a general form of y equals to ax squared plus bx plus c, where a, b, and c are constants, and a cannot be zero. Let's use graphing calculator online to plot some random quadratic functions. For example, this is the graph when a equals to 1, b equals to 2, and c equals to 3. This is the graph when a equals to -1, b equals to 3, and c equals to 5. Apparently, the shape of parabola is determined by these constants, a, b, and c. For example, the parabola is concave up when a is positive, and is concave down when a is negative. But how do I find the value of a, b, and c of quadratic function that describes the trajectory of the basketball? To do that, let's talk about science of basketball level 2, equations of motion in kinematics of particles. To simulate or predict any physics events in real life, I need to build up a model that uses mathematical language to describe physics laws. First, I set up a Cartesian coordinate system with an origin located as shown. Then I use math language to define related physical quantities. They are listed below, and pause the video to read the descriptions. Now, apply equations of motion. First, I ignore the air resistance for simple analysis. Under this condition, after the ball is shot, it'll move in two types of motion: uniform rectilinear motion and freefall motion. In horizontal direction, the ball is moving in uniform rectilinear motion, which means it goes in a straight line with constant velocity. The horizontal component of the final velocity, v sub x, is the derivative of x with respect to time, t. According to uniform rectilinear motion, this velocity is constant. Thus, v sub x equals to horizontal component of initial velocity, v sub I of x. Using trigonometry, v sub I of x is cosine of theta times v sub I. I then solve this ordinary differential equation for final position of the ball in horizontal direction, x. In vertical direction, the ball is moving in a freefall motion under the effect of gravity. The gravitational acceleration is constant g, which is negative 9.81 meters per square second. Negative means the direction of g is downward. The vertical component of final velocity v sub y is the derivative of y with respect to t. And acceleration g is the derivative of v sub y with respect to t, or second derivative of y with respect to t. I then solve ordinary differential equation 3 and 5 and get the vertical component of final velocity of the ball at any given time v sub y. Keep solving this differential equation. I got the final position of the ball at any time in vertical direction. Here I have a parametric function for position of the ball at any given time. By plotting this parametric equation, I can see trajectory of the ball by given initial conditions like theta, v sub I, and y sub I. I can also implicitize this parametric equation to a quadratic function so I can show you the connection between math and physics. Science of Basketball Level 2.5 Implicitization of Parametric Equations. In mathematics, I can implicitize this parametric function to a quadratic function so that I can identify the value of a, b, and c in general form of quadratic function. Comparing this function to the general form of quadratic function, I can learn that a is, b is, and c is. It indicates that the trajectory of the basketball is a parabola. Now let's use this function to predict the shot from the free throw line. Use the following initial conditions to shoot. Initial velocity, 7 meters per second. Initial angle, 60 degrees above the horizontal. Initial height of the ball, 2 meters. Thus, A is, B is, and C is. Using Excel spreadsheet, I plot the quadratic function. Unfortunately, the function predicts that I will shoot an air ball. And the prediction is correct. My brain tells me that I should use more strength to shoot it. But how much stronger exactly? To answer this question, I could modify function 8 to solve for initial velocity. I got, assuming the ball is released right above the free throw line, which is 4.225 meters away from the center of the hoop. So the ball must travel x equals to 4.225 meters to reach the hoop. The hoop is 3.05 meters above the ground, meaning the y is 3.05 meters. Constant g is negative 9.81 meters per square second. I release the ball at the same initial height as y sub I equals to 2 meters and at the same shooting angle as theta equals to 60 degrees. I got v sub I equals to 7.475 meters per second. Let me try it. But in reality, I don't need to shoot the ball perfectly like this. The inner diameter of the hoop is 45.72 centimeters, and size 7 men's basketball has diameter of 24 centimeters. So I can almost fit 2 balls in the hoop. To take the sizes of the hoop and the ball into consideration, let's talk about Science of Basketball Level 3 parallel curves. Look at this diagram. White dashed line represents the trajectory of the top part of the ball. Yellow dashed line represents the trajectory of the bottom part of the ball. And blue line traces the center of the ball, which is parabola. You may think that these dashed lines are parabolas too, because they are parallel to a parabola. But that's not true. Curve that is parallel to a parabola is not a parabola. In mathematics, the parallel curve is plotted by using parametric equations. X and y are the coordinates of parallel curves. C is the distance from the given curve expressed in terms of parametric equations f and g. Let's apply it with parametric equation of trajectory of the basketball. From the formula of parallel curve, f is equation 2 and g is equation 7. Thus, I can calculate the derivative of f and g. And parallel distance c is just the radius of the ball, which is 0.12 meters. The parallel curve under the trajectory of the ball is given by the parallel curve above the trajectory of the ball is given by. Notice the sign differences. At this point, there are many tools I can use to plot these parallel curves, such as MATLAB, Python, Excel, and so on. For a simple demonstration, I use an online graphing tool called Desmos. Let's have some fun with it. Here, A is shooting angle theta. V is initial velocity v sub I. D is distance from the hoop, which is x. H is initial height, which is y sub I. Then my study begins. Let's say I want to shoot a free throw. So D is 4.225 meters. By changing shooting angle slider, I can learn that the higher the shooting angle, the more likely you will make the shots. If I decrease the angle, you can clearly see that there is no much room for ball to go into the hoop. Of course, you can't just shoot with a ridiculous high angle, like 80 degrees. It requires you to accelerate the ball to insane speed within a short duration. In a jump shot, the best shooting angle range is between 55 degrees to 65 degrees. However, there are some special occasions when players prefer shooting at high angles. For example, when you're driving to the paint and there is a tall defender there. We call it floater. However, it's easier said than done. In reality, you have to precisely give the right amount of power to the ball so that it will accelerate to the right velocity. And this is when the science of basketball comes to play. Controlled by the brain, muscles have memories too. If you shoot at the same spot many times, it'll remember how much power is required to make the shots. I can use this interactive diagram to find the initial velocity of my shots at my hot zones. For example, I often make three-point shots with 60 degrees. Calculated from the science equations, the initial velocity is about 9.2 meters per second. That means whenever I'm ready to shoot from three-point line, my muscle will remember how much power it should provide, and it will accelerate the ball to 9.2 meters per second. I mean, roughly. But now, with the help of science, I can use the same muscle memory to make a floater at 80 degrees when I'm about 2.8 meters from the hoop. I can also make a fadeaway shot at any spot that has the same distance of free throw line to the hoop. In this way, there are 3 different ways to score with the same muscle memory. Of course, you must practice these different shots too. Science is just a tool to assist you, but you still need Black Mamba mentality to be the best version of yourself. Besides having fun with this interactive diagram, I have done other studies with Excel too. Here I made a plot of initial velocity versus shooting angle with initial height y sub I as 2 meters, 2.5 meters, and 3 meters, and labeled with short, tall, and pro players. Learn from the plots, the higher the initial height you release the ball, the smaller the initial velocity is required to make the shots. That means for taller players, they can shoot with less power than short players do. Don't underestimate that little power saving. The saved power from shooting can be used for other part of the game like defense, fast break, and so on. Congratulations, you have become an amateur hooper scientist. But this is nowhere near to the end of study of science of basketball. I will study bank shot, including science topics like inelastic collision and coefficient of restitution. Ultimately, I will combine kinesiology with kinematics of rigid body to understand how lower limb work together with upper limb during the motion of shooting. Topics will include general plane motion and dynamic simulation. If you like this topic, please give the video a thumbs up and subscribe to the channel. See you next time.